So I wanted to finish the Simulink diagram that I was doing last time. We had the three transfer functions that were the solutions for our example. So we entered those into these transfer function blocks, numerator and denominator polynomials. We set up a unit step up and a unit step down of 1 degree. We'll look at the plot. I think we should be good there. Convert it to radians because our equations require radians. And then we're going to scope the output. So I already drug a scope down here for the elevator. We can get output scopes for the other variables as well. I'm going to copy and paste. I'm not going to copy. Let's see. Highlight, copy. There we go. So I can put a scope as an output for each one of these. I can label these. This is alpha. This is velocity. And this one is theta. Oh, and I need to convert to degrees because we're in radians. So let me put some conversions in here. So these are multiplier box. So I have to multiply by 180 and divide by pi. And if I've done everything right, I can go up here and click the run button. And it will run this forward in time for 10 seconds. That's the number up here. And I want to increase that to 50 seconds. Click run. Oh, I want to pop the scopes up here. So if you click on these, you get the scopes opened up. And I need to share my whole screen here. So you can see everything. So I've got a double click on the U scope and it pops up. Same thing with the alpha scope. Popped up over on my other screen here. And the theta scope. And the elevator. I'm going to have to drag each one of these out individually. So I'm going to leave the elevator here. I'm going to click run. And it ran. You guys can see this, right? Oh, I need, yeah, we're sharing screen, right? Yeah. So on Zoom, you guys can see these scopes? Yes? Anybody here? Huh?
I cannot see it on Zoom.
How about now?
Still nothing.
So you're seeing the screen over here. Oh, I'll pop through each one individually here. I've lost my Simulink. Okay, now I think I can do this. All right, so there's, you guys can see that, right? On Zoom. Your what? Why? So do you see that? A scope, an elevator. Yes?
Yes, I can see it.
Okay. That's weird. Okay. Still new technology, even though I've been using it for 3 months. Anyway, so inside the Simulink diagram, we put the scopes. You guys saw that happening, right? The U, alpha, and theta scopes. This is the elevator scope. So I went up here and I changed the stop time to 50 and I clicked run. And you're seeing the elevator scope. Is that correct?
Yes, sir.
Do you see the Simulink diagram?
At the moment, it's just the elevator scope.
Okay, so you can see the elevator went up to 1 and back down. So I'm going to close that out. Now let me share the screen that shows the angle of attack. So this is the angle of attack response. When the elevator kicks in, we get a spike down, a spike up, and that's the oscillation. And so what you're seeing here is the short period mode, that high frequency mode that we talked about last time. In fact, if we look at this and count one full period, it looks like it takes about 3 seconds to go through a period. So remember that number, because we're going to go back to our frequency and see if that matches for the short period. Here's the theta plot. Notice in the theta plot, we see the short period mode, and we see this longer mode, the Phugoid mode. That's the low frequency, high, long period mode, Phugoid. So in theta, we see both modes. In alpha, all we saw was a short period. And in the U mode, we don't really see much short period mode, but we see the long frequency Phugoid mode. So this is key. It looks like the short period mode occurs in alpha and theta, but not U. So we can use that to our advantage in making an approximation for that mode, because experiments and these simulations say, okay, well, we don't need to consider velocity in the short period mode. So we can throw that degree of freedom away and limit this solution to just 2. So we'll do that in a minute. Whereas for the Phugoid mode did not show up in alpha, but it showed up in velocity and theta. I got that right? I think that's right. And so we can eliminate the alpha degree of freedom on that one and solve just a 2x2 problem. So that's how you can use Simulink to simulate a system. You create blocks that could do the transfer function. You put an input in, whatever you want to put in as the elevator, and then the output here is the time response of the different variables. And again, inside Simulink, it's solving this Laplace transfer function and solving it in the time domain for you, so it's integrating it over time. So now we want to talk about those approximations. But I want to write that on the board real quick. Because what we observed from those plots, and people saw this in experiment as well, is that the Phugoid mode was mainly in the velocity and theta, not much angle of attack. Whereas the short period was mainly in alpha and theta, not much in the velocity. Yeah, and so what's going on here is the short period mode happens so fast that the velocity, the inertia of the airplane doesn't allow the velocity of the airplane to change that quickly. So you don't get much change in velocity. So we can take that advantage of that, and we can say we'll do a short period approximation where all we do is look at alpha and theta. And then we'll do a Phugoid approximation where we simply look at u and theta. So I'm going to pop up the matrix problem, the 3x3 that gave us those complicated transfer functions, and see how we can use that information to our advantage. So if we go back to your handout where we developed the matrix problem, this is the 3x3 matrix problem that we solved for the three transfer functions, u, alpha, and theta, and those were the transfer functions that we were just simulating. Well, if we first say, okay, we can say the velocity is constant for the short period, that knocks out this degree of freedom. And that gives us three equations and two unknowns. So we can get rid of one of the equations. And the one most naturally correlated to velocity is the drag equation. So we knock out the drag equation, which is the top row, and we knock out the velocity degree of freedom, which is this column, and that leaves us the 2x2 problem that I've done in the blue. So down here, we're going to grab this and just put that, this is in your book, I've done a correlation of compiled, there we go, compilation of several different pages. So you grab just those 2x2 part of the matrix, the z-force and the pitching moment equation, and we solve for these two unknowns. So this is a lot easier. Kramer's rule means we just take the determinant of this 2x2 matrix, and that's the denominator polynomial that gives us the roots. And that gives us the short period approximation. So notice that there's a couple other assumptions that he does, and I've done those in red here. He says z alpha dot is small to reduce this, zq is small, and we're going to say that we're flying at a pretty shallow flight path angle. and he combines these two M alpha terms into one. It just means you have to add both of them together. So back to the board, we're going to write down the determinant of that because that is the denominator polynomial that gives us the Phugoid, sorry, the short period approximation to that second order mode. So we're doing this one now, the short period approximation. And with that 2x2 problem, we multiply do the determinant calculation and do some algebra. Oh, let's see, I jumped ahead one. Let's go step by step. So just taking the straight determinant, so there's the polynomial, and we can factor an S and a U1 out of here, because notice there's an S and an S here, and there's S's in both of these terms, so we can factor this whole thing out of the whole thing to get the second order polynomial. And this thing in here is the short period approximation mode. Notice I put it in S squared S and then the constant term because that's how we're going to identify the natural frequency and the damping ratio. And you can see how this is a lot easier than calculating A1, B1, C1, D1, and E1, right? And then getting that fourth order polynomial and then finding the roots of that. Then we look at this and we compare it to standard second order form. And this thing here has to be the natural frequency squared. And this thing here, this whole bracket here, has to be twice the natural frequency times the natural frequency times the damping ratio. And usually we'll put a subscript SP on these to mean short period. So hopefully you can see that. So that means the natural frequency is the square root of this thing. And the damping ratio and so it's an easier calculation. So if you're designing an airplane and you want to say, okay, well, what about this configuration for my airplane? What's my damping ratio, short frequency, short period? You do a few changes, you calculate a couple of the dimensional derivatives and you're done. And you can say, oh, I got a good damping ratio with this configuration, but not this one. And then you do the full-blown 4x4 analysis on the whole thing. The other thing you can say is, okay, well, my damping ratio of my current airplane is too low. What can I change to fix that? All right, that's a preliminary design question. You know, I've designed an airplane, oh, the damping ratio is bad. What do I do to fix that? And you can look at this and say, oh, look, MQ So this is tied to CMQ. That's the pitching moment caused by a pitch rate. And you know that this is related to the horizontal tail size and location. So that means, okay, I need to make my horizontal tail bigger, or I need to move it further back. So that's the tracing you can do with these simple approximations that are harder to do with that full 4x4 problem. I mean, these terms still show up in the 4x4, but they're mixed in with so many other things. You could also say, okay, well, I need to fix up Z alpha maybe. Although that's divided by U1, so that tends to be a smaller effect. So immediately you can use the approximation to hone in on that and say, I can fix my short period by doing this. In the next homework, you'll calculate the roots for that BizJet. I told you you'd calculate the coefficients and the roots, do the state space and all that. We'll calculate the roots by the full-blown method and also by this and compare them and see how well they match up for that airplane. And they do match up pretty well. And then there's the Phugoid approximation, which comes from that other assumption that says that U doesn't change very much. No, sorry, that's the other way around. Alpha doesn't change much. So we go back to this, and in this case, we say alpha, we're going to throw it away because we saw in the plots and experiments, flight tests show that in that mode, you don't see much alpha change. And so we're going to throw away the middle column. It's going to knock this out, which leaves two unknowns, but still three equations. So then we have to say, well, which equations do we keep? And people have tried various combinations, but it turns out that if you throw away the pitching moment pitching moment equation, and only keep the lift and the drag equations, then you're good. And that fits because the drag equation is correlated to the speed, and the lift equation is more correlated toward theta. Whereas alpha is tied to the pitching moment pitching moment equation through CM alpha and some of those other important stability derivatives. So we keep the stuff in the green squares. Throw away alpha, throw away the pitching moment equation, and you get this 2x2 problem. And again, make some approximations. ZQ is small, theta is small. Combine these two together, and you get another second order system that you put into standard second order form, and you get the damping ratio and the natural frequency of the Phugoid. So in the Phugoid, this one's even easier. You multiply it out, divide by U1. And then this thing is the natural frequency squared. And this thing is twice the damping ratio of the Phugoid times the natural frequency. And we get approximations for those. And again, it's a faster calculation if you're doing preliminary design. And you can look at this and say, if I need to change my damping ratio, I'm either going to have to make my natural frequency smaller through ZU, or I'm going to have to fix up XU. And both of these are the Mach number type perturbations, CLU and CDU. So in all honesty, there's not a whole lot of major design changes you can make that affect these a lot. But the Phugoid mode tends to be more benign because the frequency is so slow that pilots just compensate for it as it goes along. And you'll see that when we look at the federal aviation regulations, that most Phugoid modes are just fine, and there's a lot of latitude in designing for that. So for the longitudinal modes, we took the 3 longitudinal equations, we plugged in the forces and moments, rearranged it, took Laplace transforms, put it into a matrix so we could solve it, came up with transfer functions, found out that's a lot of work, came up with some approximations that make sense based on experiment, and have these approximations. So we're going to do the same thing lateral directional. Same exact process, the other 3 equations. And so that's the handout that you have today. So now we're looking at these other 3 equations. Same process, we need to plug in the side force here, and we need to plug in the rolling moment model and the yawing moment model that we developed in chapter 3. And we're going to use P is equal to phi dot and R is equal to psi dot, because again, we're going to assume that this is small. We're flying at level flight, so we're in our level cruise condition. So P is phi dot and R is psi dot. Going to plug in, here's our lateral directional forces moment model in terms of beta, beta dot, P, R, and aileron and rudder. And we have to throw in the thrust force model, which doesn't have a whole lot, it just has beta. So I'm going to do the first equation. Just to demonstrate that process again. And then we'll assume that we could always do the other. I circled the wrong equation, didn't I? Switch colors. We're going to do this one. We're going to do the side force equation. So you remember the process? Substitute the force and moment models. So we're going to substitute the force models in here. We're going to divide by m. We're going to collect terms together that are just numbers and define those dimensional derivatives. Then we're going to Laplace it. Then we're going to stick it in a matrix and solve it. And you're saying I got a beta dot here, but the equation has a v dot, but v dot is u1 times beta dot, because the side velocity, beta is the side velocity divided by u1. We did that a long time ago. Here, there's phi dot. That's where this was p before, and we plugged in phi dot for that. And there used to be an r here, but now it's psi dot because we used that. So this is the side force perturbation equation. Everything else was just the dynamics. We divide by m because there's m here and we can divide through it and it's going to cancel some of the m's out. And then we collect terms together. I lost a phi. Stick a phi in here. That's just from the equation. So here we divided by m, so we get a q bar s divided by m times cy beta. And I collected all that stuff together here. Multiplied times beta. And then here's all the stuff that multiplies beta dot. Here's all the stuff that multiplies phi dot. Now we're going to go over here, do some more stuff. This is all the stuff that multiplies r. It's all the stuff that multiplies aileron. All the stuff that multiplies rudder. And now we're going to name stuff, because we're tired of calculating all these numbers every time and writing them down. So we're going to call this something that we pre-calculate. It's the side force equation, so I'm going to call it y. And it multiplies beta, so I'm going to put a subscript beta on it. And I'm going to call this y subscript beta dot. And I'm going to call this y, and what subscript do you think we ought to put on this? multiplies phi dot, right? So we could put a phi dot, but it's actually the p effect. So people tend to call this yp. It wouldn't be wrong to call it y phi dot. Oh, I forgot, r here is multiplied. Well, we change r to psi dot, so make sure you fix that up, that thing right there. And we're going to call this, same reason, we're not going to call it subscript psi dot, we're going to call it subscript r, because it's the yaw rate. We're going to call this y delta A. And that's y delta r. And again, in your book, and the next page in the handout that I gave you is the definition of all these derivatives, these dimensional derivatives, just like we had for longitudinal flight. And again, the reason we define those is because they're all just numbers. You plug in the numbers for all of the values, and you calculate a number ahead of time, and that way it makes it easier to write that matrix problem. So you've got that in your handout and in your book. And so it makes this equation a lot easier to write because it's u1 beta dot plus u1 psi dot equals g phi cosine theta, y beta beta, y beta dot yp, phi dot, so on. And it makes it a lot easier when we go to Laplacing it. And notice that I've shoved all of the variables on the left side and kept the inputs on this side. So I'm setting it up to put it in the matrix formula. Because in the matrix, we're going to have all of the unknowns over here, and then the inputs or the known stuff are over here. And in your book, he neglects this thing. He says, well, this is usually pretty small, the side force. So you'll see that not in the book. I included it so you can see if you need to include it, or the other equations will keep that term. Like the rolling moment will keep a beta dot term. That's how you do it. So step 2 was to divide by m. Step 3 was to define the dimensional derivatives. Step 4 is to Laplace. And we do this with 0 initial conditions because we're saying initially we're flying at cruise. So all the small perturbation variables are 0, and then something happens. So you get u1s beta of s plus u1s psi of s minus g. Phi's the variable here. Cosine theta just goes along for the ride. And notice we've included the option of having aileron input, rudder input, or both. In the formulas that he went from this point on, he says, well, you have to choose one or the other. And I'm just going to call it delta. So instead of keeping both inputs on the right side, he calls it y delta times delta, and you choose whether delta is the rudder or the aileron. And that way you just get transfer functions for those. And either one will feed into the input. You can turn the aileron on and the rudder off, or the rudder on and the aileron off. And so put this into a matrix form. So here's the unknowns. There's 1, 2, 3, still the same. So our unknowns are and again, it's Laplace, so it's algebraic. So we're going to have a matrix that we solve for these. And just like before, he divides both sides by the input so that we're solving for transfer functions. So again, we went faster this time because we've already done this before, and you've done this in homework, right? I'll give you a minute to catch up here. Yeah. With the formula he has, the solutions, it's just one or the other. Can't do it. I mean, you could do it if you went back and put both of them in together, change the equations. But it makes more sense than you might think. You say, okay, I want to see, well, what is the response to a step rudder input? Or I want to see what's the response to a step aileron input. And you just look at those two independently. So again, we're not looking at, like trimming the aircraft in any kind of a steady state using both rudder and aileron like we did for the one engine inoperative, right? We needed both. We're just saying, okay, you're flying along in whatever cruise condition. What happens if I spike the aileron? What happens? What if I spike the rudder? And they both excite all the modes. So back to your handout. There's the dimensional derivatives. You've seen those. There's the three equations. We did the top one. Notice that he defines some additional parameters here. A1 bar and B1 bar are these inertia ratios. So if you see those in the equations, that's where you find out what they are. This is the equation we Laplaced. You do the same thing for the other two. Throw them into a matrix. So here's the unknowns, beta, phi, and psi. This is just collecting the proper terms and putting them in the right places. And then here's the generic delta that could be rudder or aileron. So then how do we solve this? Kramer's rule. So you replace, to get beta, you replace the first column with the right-hand side, determinant on top, and then the determinant of the whole matrix here on the bottom. So the determinant of this matrix gives you the roots of the denominator polynomial of the transfer function. So those are the roots that give us the response. To get phi, you replace the middle column. And to get psi, you replace the right column. And so in your book and in your handout, here's the solutions. Here's the beta transfer function in terms of the right-hand side being here. He gives you a formula for the denominator polynomial and all the coefficients, just like longitudinal. There's the numerator polynomial for beta. I gave you all that in the handout, right? I copied these pages. They're in your book as well. And I didn't give you the pages that have the phi and psi, but they're similar to this. So you have all of the formulas there. Again, it's a long process, not impossible, but you calculate all the dimensional derivatives like we talked about last time for longitudinal, and then you stuff them in here and calculate A2, B2, C2, D2, and E2, and then you can find the polynomial, and then you can find the roots. Or you can put this in state space form and do that other process, which is nice. So let's look at the BizJet again. We're not going to go through the whole mechanism of calculating it because we've done that once, and I'm confident you guys can plug numbers in formulas and calculate them. But if we look at the BizJet and calculate these coefficients for that BizJet example, let's look at the roots we get. So now we're looking at the BizJet. By the way, I learned a long time ago that the abbreviation for business jet is not bus jet. You would think it would be, right? I started to write that one time in class, and I looked at that and go, that's not right. Because it sounds, well, I guess it would be an Airbus jet then, right? So if we look at a BizJet, that BizJet example in the book, and we calculate these parameters, here's what we get. Oh, sorry, this is 2 because it's lateral directional. So you look at that, and those coefficients, is it stable or not? Correct answer is I have no idea, but you do have a little clue, right? Routh-Hurwitz criteria says they have to be all the same sign. So that's a good sign. We could do the Routh array on this, or we could just solve the polynomial roots in MATLAB. So if we use MATLAB and get the roots, the algebra guys say we have all real coefficients, so we get 2 complex conjugate pairs. If I'm going too fast, somebody say something. I'm going to scroll up. Am I good? Somebody groan and shout if I'm not. So here's the roots, right with them with a lot of space in between because we're going to talk about them. So there's the first set. Oh, I'm wrong. We don't get two complex conjugate pairs. We get one complex conjugate pair and two real roots. Here's what they are. I was still stuck on longitudinal. So we look at this, and this one is obviously stable and oscillatory. This is barely stable. And this one is definitely stable. So we could call them that. We could say this is the stable oscillatory mode, the barely stable mode, and the definitely stable mode. But it turns out that this bottom one is really related to the airplane rolling. And it's so well damped because the big wings stick out on either side, and if the airplane starts to roll, those wings sweep through the air and stop the roll, and that's the damping. And it's so damp that there's no oscillation at all. So this is called the roll mode. And the barely stable mode sometimes is actually unstable, and it's okay because it's a slow spiraling of the airplane away from the intended direction of flight. But it happens so slowly, as long as you're not too unstable, and that's a requirement, is that if it just barely drifts away, the pilot corrects for it or an autopilot takes care of it. And this stable oscillatory mode, you guys all know the name of it, right? The Dutch roll mode. And it's this weird banking, yawing, side-slipping motion similar to the Highland Fling that I show you in the 514. That's the ride. No, Highland Fling's at Six Flags, Zulus at Worlds of Fun. So these are the normal modes of a conventional airplane. You don't have to get those, just like the longitudinal modes of the jet fighter were not Phugoid in short period. But normally you get these modes, and then the FAR regs will tell you if this is enough damping, and how about this frequency? Is that good or bad? And in fact, we'll have to convert the damping and frequency into damping ratio and natural frequency to compare it to the charts. Just like longitudinal, there are approximations to these modes, and we'll talk about those next time. But with the rest of our time, I want to turn back the exam, and we'll go through how I graded that so you can take a look at it. So Aaron, I'll head that way and call some names. Ahmed, I'll come around and get you. Rutha. Sam D'Souza. Laura. Ryan. Stephen. Linda. How convenient, you guys are right next to each other. Cord. Is Cord Byers here? Brendan. Tree. Keegan. Keegan here? Cole. Thought I saw you come in. Jonathan. Austin. Kyle. Wasik. William. Maripong. D'Souza. Sam. I think I'm back to the beginning. So the first thing you should note is that when I graded this, and then I finally added it up, I realized I only had 45 points assigned. So your grade divided by 45 turned into a percent, and then divided by 2 gives you your final score out of 50. Did that make sense? So your total should be the number written above 45. Make sure I totaled it correctly. Actually, make sure our student assistant totaled it correctly. And then make sure I graded it correctly. So the first problem is the pitch rate effect on pitching moment. So what I was looking for was a diagram that showed the horizontal tail back here. And you didn't have to use XH. Some of you used XACH minus XCG. That's okay. But you needed to show some kind of moment arm that was worth 3 points. You needed to show positive pitch rate like that. And then say that a change in angle of attack of the wing sweeping down produced a force. So this was worth 3 points, 3 points, and 3 points. And then you needed to do an explanation that says that a pitch rate produces an alpha of the tail, which gives that force that you drew. You didn't have to write the equation. You just say the force acting behind the CG gives a negative pitching moment. So positive Q. So that was where you were showing the sign of the effect. And this was worth an additional 3 points, this transition, and then this, that you're behind the CG and you get a negative pitching moment. Did you like that problem or did you hate it? I guess it depends on how well you did on it, huh? Next problem was the total calculation problem. So 5 points for calculating alpha. You have to convert alpha. You have to calculate alpha dot C bar over 2U1. So the numbers that you should have gotten for this. So that was worth 5 points. And then sticking that all into the CM equation. And then calculating the final answer. That was the other 5 points here and 5 points there. So that's how that one was graded. And then for the one engine in operative condition, here's our airplane. We've got one engine cranking away, one engine dead. So there's some drag. So that's going to create a yawing moment like this, which is not M. And so you're going to need a rudder deflected positive to produce a negative yaw to cancel that out. And that's exactly what you needed to write for part B, is that the negative N from the positive rudder cancels the positive N from the one engine in operative condition. Points for that, 5 points for the diagram here. I looked for the thrust and the positive rudder on this. I was going to look for this, but if you put the thrust in there, I gave you full credit. And then 5 points for the explanation here. Needing both of those, that the negative N from the rudder cancels this, or you could say you got this from the engine out condition, so you needed the rudder. Either one works. And then the last part is, well, what kind of aileron do you need? And fundamentally, the positive rudder produces a positive rolling moment. And so you need to counter that with a negative aileron to stop the roll due to the rudder. And that was worth another 5 points. Any general questions? Again, I'm always happy to talk with you during office hours. I have office hours tomorrow morning or before class on Tuesdays and Thursdays. I'll be happy to take any specific questions, comments, arguments, discussions, whatever. So for the rest of the class, we have like a week and a half, right? This week, and then next week, and then we've got Thanksgiving, and then we go online. And I'm grateful that we made it to Thanksgiving. Although cases are going up, I think we've been pretty careful in WSU and in class, and people have followed the mask mandate, so thank you all for doing that. You have a flight test assignment due next Tuesday. And then we're doing an exam over the material through pretty much right now. We'll be on this exam. I've assigned another homework, and that's not due until the Thursday after Thanksgiving. So you'll turn that in online, and it'll be graded just like you're doing anything. And then the final is scheduled for December 10th, just during the normal time for the final for this class. And I'm still trying to figure out what format I'm going to go with on the final. So I'll figure that out. It will not be write your name on a piece of paper and you get full credit. There will be some work to do. All right, I'll see you on Thursday. Everybody have a good evening.